There are two quantum mechanical theories used to describe covalent bond formation and the electronic structure of molecules. However, we focus more on valence bond theory, which describes how bonding occurs. According to valence bond theory, a covalent bond forms when two atoms approach each other closely and a singly occupied orbital on one atom overlaps a singly occupied orbital on the other atom. The electrons are now paired in the overlapping orbitals and are attracted to the nuclei of both atoms, thus bonding the atoms together. Let us start our discussion of valence bond theory by considering the formation of an H2 molecule from two H atoms. The H2H bond results from the overlap of two singly occupied hydrogen 1s orbitals. Initially, when the two atoms are far apart, there is no interaction. We say that the potential energy of this system is zero. As the atoms approach each other, each electron is attracted by the nucleus of the other atom. At the same time, the electrons repel each other, as do the nuclei. While the atoms are still separated, attraction is stronger than repulsion, so that the potential energy of the system decreases as the atoms approach each other. This continues until the potential energy reaches a minimum value. At this point, when the system has the lowest potential energy, it is most stable. This condition corresponds to substantial overlap of the 1s orbitals and the formation of a stable H2 molecule. Valence bond theory gives a clear picture of chemical bond formation. It states that a stable molecule forms from reacting atoms when the potential energy of the system has decreased to a minimum. The concept of overlapping atomic orbitals applies equally to diatomic molecules other than H2. Thus, a stable F2 molecule forms when the two p orbitals in the two F atoms overlap to form a covalent bond. Similarly, the formation of the HF molecule can be explained by the overlap of the 1s orbital in H with the 2p orbital in F. In each case, valence bond theory accounts for the changes in potential energy as the distance between the reacting atoms changes. An isolated atom has its electrons arranged in orbitals in the way that leads to the lowest total energy for the atom. Usually, however, these pure atomic orbitals do not have the correct energies or orientations to describe where the electrons are when an atom is bonded to other atoms. When other atoms are nearby, as in a molecular ion, an atom can combine its valence shell orbitals to form a new set of orbitals that is at a lower total energy in the presence of other atoms than the pure atomic orbitals would be. This process is called hybridization. The concept of atomic orbital overlap should apply also to polyatomic molecules. In this section, we will discuss three examples of valence bond treatment of bonding in polyatomic molecules. Consider the CH4 molecule. We can represent the orbital diagram of the valence electrons of C as, because the carbon atom has two unpaired electrons, it can form only two bonds with hydrogen in its ground state. Although the species CH2 is known, it is very unstable. To account for the 4 CH bonds in the methane, we can try to promote or energetically excite an electron from the 2s orbital to the 2p orbital. Now there are 4 unpaired electrons on C that could form 4 CH bonds. However, the geometry is wrong because 3 of the HCH bond angles would have to be 90 degrees. Remember that the 3 2p orbitals on carbon are mutually perpendicular, and yet all HCH angles are 109.5 degrees. To explain the bonding in methane, valence bond theory uses hypothetical hybrid orbitals, which are atomic orbitals obtained when two or more non-equivalent orbitals of the same atom combine in preparation for covalent bond formation. Hybridization is a term applied to the mixing of atomic orbitals in an atom, usually a central atom, to generate a set of hybrid orbitals. We can generate 4 equivalent hybrid orbitals for carbon by mixing the 2s orbital and the 3 2p orbitals. Because the new orbitals are formed from 1s and 3p orbitals, they are called sp3 hybrid orbitals. These 4 hybrid orbitals are directed toward the 4 corners of a regular tetrahedron. Thus, CH4 has a tetrahedral shape and all the HCH angles are 109.5 degrees. On the other hand, beryllium chloride or BeCl2 molecule is predicted to be linear. The orbital diagram for the valence electrons in beryllium is: we know that in its ground state, beryllium does not form covalent bonds with chloride because its electrons are paired in the 2s orbital. So we turn to hybridization for an explanation of beryllium's bonding behavior. First, we promote a 2s electron to a 2p orbital, resulting in... Now, there are two beryllium orbitals available for bonding, the 2s and 2p. However, if two chloride atoms were to combine with beryllium in this excited state, one chloride atom would share a 2s electron and the other chloride would share a 2p electron, making two non-equivalent beryllium chloride bonds. This scheme contradicts experimental evidence. In the actual beryllium chloride molecule, the two beryllium chloride bonds are identical in every respect. Thus, the 2p and 2s orbitals must be mixed or hybridized to form two equivalent sp hybrid orbitals. These two hybrid orbitals lie on the same line, the x-axis, so that the angle between them is 180 degrees. Each of the beryllium chloride bonds is then formed by the overlap of a beryllium sp hybrid orbital and a chloride 3p orbital, and the resulting beryllium chloride molecule has a linear geometry. Next, we look at the boron trifluoride or BF3 molecule, known to have a planar geometry. Considering only the valence electrons, the orbital diagram of B is: first, we promote the 2s electron to an empty 2p orbital. Mixing the 2s orbital with the two 2p orbitals generates three sp2 hybrid orbitals. These three sp2 orbitals lie in the same plane, and the angle between any two of them is 120 degrees. Each of the BF bonds is formed by the overlap of a boron sp2 hybrid orbital and a fluorine 2p orbital. The BF3 molecule is planar with all the FBF angles equal to 120 degrees. To summarize our discussion of hybridization, we note that the concept of hybridization is not applied to isolated atoms. It is a theoretical model used to explain covalent bonding. Hybridization is the mixing of at least two non-equivalent atomic orbitals, for example, s and p orbitals. Therefore, a hybrid orbital is not a pure atomic orbital. Hybrid orbitals and pure atomic orbitals have very different shapes. The number of hybrid orbitals generated is equal to the number of pure atomic orbitals that participate in the hybridization process. Covalent bonds in polyatomic molecules and ions are formed by the overlap of hybrid orbitals, or of hybrid orbitals with unhybridized ones. Therefore, the hybridization bonding scheme is still within the framework of valence bond theory. Electrons in a molecule are assumed to occupy hybrid orbitals of the individual atoms. This table summarizes sp, sp2, and sp3 hybridization.